Hello, my name is Dr. Sean Argyle, and the following presentation, entitled Mathematical Thinking from Cacophony to Consensus, is a defense of my dissertation. You may ask yourself, what is mathematical thinking? And in fact, that's the very question that got me started in the first place. And the problem is, all these words that you see in the word cloud on your screen are used to describe the same basic phenomenon. And no two authors really seem to agree. It was total chaos. Back in 2010, when I was just starting my dissertation, I was honored with the privilege of asking President Obama about what it means to be an educated person. You can click the link to go see the video. But in short, he said the most important thing a kid can learn in school is how to learn and how to think. This conversation helped me pick my topic in the first place. If the most important thing is how to think, well, how do you think? And as I said before, the research community did not really have a good answer to this question. The lack of a good definition is a real problem because, as you can see here, standards documents such as NCTM's 2000 Principles and Standards use the phrase, but then never really define it anywhere. How can a teacher improve a student's mathematical thinking if they don't know what mathematical thinking is? The more recent Common Core Standards, while a step in the right direction, still just provides mathematical thinking in this sort of unordered list. Does making sense necessarily come before modeling? Does attending the position always come after reasoning abstractly? This list, while important pieces of mathematical thinking, doesn't really allow the teacher to think about and plan for the way students think mathematically. The situation became so bad that Ed Silver, a past editor of the Journal for Research and Mathematics Education, a really big journal for math education, said mathematical thinking means whatever the author chooses it to mean. In other words, for every researcher there was a different definition, and if that wasn't bad enough, for some authors there were even more than one definition. For example, here are two different definitions of mathematical thinking from a researcher by the name of David Tall. In 1992, he talked about mathematical thinking as a negotiation between the internal representation of mathematics and the external formal representation of mathematics. However, a decade later, in 2004, he talked about it as a linear process going from human experience to very formal axioms and properties. When you think about it, you realize that the 2004 definition is a linear process and is in stark contrast to the cyclical model of going back and forth between internal and external representations. Not only has his vocabulary changed, but the basic structure of his model is completely different. This lack of a good definition, or any agreement in the literature, made me think back to my undergraduate class on the philosophy of natural science, in particular, a book by Thomas Kuhn named The Structure of Scientific Revolutions. If you've ever heard the phrase paradigm shift, this is the book that started it. Kuhn says science proceeds in this cyclical pattern of having some ideas, testing them out and getting some good results, then starting to get more and more unexplainable results, and ultimately you have a revolution, such as when we went from Newtonian physics to Einsteinian physics. It wasn't that Newton was wrong, it's just that Einstein came up with completely new definitions of things like time and space, which made us see the world in a completely new fashion. But before you get into this cycle, Kuhn says you have a period called pre-science. Kuhn's definition of pre-science basically describes verbatim the situation I uncovered in mathematical thinking. Nobody agrees on a definition, everyone has a completely different definition, and their lines of research really don't overlap and build on each other. I realized what we really needed as a research community was a strong, paradigmatic definition of mathematical thinking to which just about everyone could agree and proceed forward with their research. But whose definition should I pick? Should I pick David Tall? Schoenfeld? Wiener? Dubinsky? There were so many choices, and there was no real way to say that anyone was better than all of the others. This problem reminded me of something W.V.O. Quine once discussed. He said, "What does this phrase bachelor mean? I suppose we could define it as unmarried man, but then you get silly things like Bachelor of Arts becoming unmarried man of arts, and no one would ever say that. Also, bachelor has a different number of letters. It has different kinds of letters in it. It just really isn't always interchangeable, one for one, with the word bachelor. Do we just open up a dictionary and say, that's it? Well, do we use the Oxford English Dictionary, or do we use Webster's Dictionary?" This inability to decide between different definitions of mathematical thinking as one being better than the other made it very difficult to do a traditional empirical study. Originally I thought, hey, let me just study some mathematicians and see what it is they do, because the other researcher really only goes to undergraduate students. And hey, if anyone's doing mathematical thinking, it's professional mathematicians. But how do I devise a coding scheme if I can't even come up with a definition for what mathematical thinking is? And how do I compare algebra to geometry to physics? What if there are subconscious elements? There was just no way to do this kind of traditional research without starting from a definition. So I began to consider using a methodology that was more theoretically oriented, such as grounded theory or phenomenology. They still had some empirical elements, but they would allow me to get at some of the harder to describe quantitatively elements such as subconscious and culture. But the problem with these is they take a long time. It's hard to define and track down all the people that would influence a person. Maybe his 8th grade math teacher is retired. How would I get that participant's full culture described? It just wasn't appropriate for a dissertation piece of research. And it didn't really study mathematical thinking so much as my perceptions of mathematical thinking. And while that's not a bad thing, as I described, there's already a lot of people out there describing their perceptions of mathematical thinking. My particular definition as an untested doctoral student simply wasn't going to become the new paradigm. Ultimately, I realized the best solution was to go with a meta-analysis. Rather than studying people directly, I would study the articles that had already been written. The upside is that this is theory, and I don't have to say Schoenfeld is better than Wiener or vice versa. Moreover, in getting towards a new paradigm, I get to stand on the shoulders of giants and say, this isn't just my idea of mathematical thinking. This is the idea of 100 or 200 or however many articles I would end up picking. And I get all of their credibility. Moreover, it condenses a decade or more of research into a reasonable dissertation timeline. The only downside here is that it's not directly empirical. It's only empirical in that some of the studies in the meta-analysis might be empirical rather than theoretical. My guiding research questions were essentially, is there any consensus out there in this huge morass of information? All these different definitions, can I at least break them down into categories? So instead of 100 definitions, I actually have 3 or 4 categories of definition. Can I do better than that? Can I get just 1 or 2? And if I do find any consensus, well, what does that mean? Because it's not good enough to just come up with a definition. It has to be a definition that is meaningful and has some practical implications. Moreover, I had to break down all of the data that would be available to me into more parsable chunks, because I couldn't read 100 or 200 articles all at the same time with the same level of analysis. So I ended up breaking it down into categories: model, contrary, borderline, non-case, which in short start with the articles that are very much focused on the topic of mathematical thinking, are actively researching it and discussing it, working your way down through those who kind of mention it or use the concept, to the people who don't talk about it at all. And I like that in my particular case, this breakdown became somewhat normal. Of course, the other problem to consider with a meta-analysis is, how do you do it? If you've got all quantitative data, the answer is very easy. There's very well established statistical methods where you take, different studies and you put them together, you shuffle some numbers around, and you come up with a new, better, stronger statistical result. Except, as you can see here, in the data that I was looking at, a great deal of them were theoretical. And even those that had a more formal methodology, such as the constant comparative method or teaching experiment, they were still very qualitative and tended to use the data to reinforce the ideas they had coming in with. There was no bottom to it. You couldn't just say, this is where the idea started from, this is the data that started it all. And so I needed a way to put together theoretical, philosophical ideas together, and that was very difficult. In the end, I used a methodology called conceptual analysis. In particular, I used the book Thinking with Concepts by John Wilson to guide me. And the underlying concept here is that we don't care what the official definition is, if there's a true definition. Rather, we want to know how is it actually used in everyday life. And that's sort of how lexicographers who write dictionaries in the first place go out. They go out, they see how it's used in conversation and how it's used in books, and they say, this is the definition of the word. That's what I did. I looked at these research articles. How are they talking about mathematical thinking? What other words did they associate with mathematical thinking? The source of the articles for my meta-analysis was the journal Mathematical Thinking and Learning. First of all, it's got a great title, but even better, if you look at the research foci, every single point there has something along the lines of mathematical thinking right in there. That means that virtually every article should be at least a little bit related to mathematical thinking. This is in contrast to bigger, more prestigious journals such as JRME and the Journal of Mathematical Behavior. I could have selected those and I would have had many more articles to choose from, but not nearly as many of them would have been actively addressing mathematical thinking. What I did then was I took copious notes on the contents of all these articles, and then I snipped them up and filtered them into a whole bunch of different envelopes to get at main themes. I had something like 1,000 different notes, and I separated them out into categories, and sometimes the categories would overlap, and then so I'd throw them into the blender again and put together perhaps cultural concepts with goal making or motivation, and just kind of slewed them together in a big old Blendtec blender until I got it down to what I felt were the most essential categories that I couldn't simplify any further. The table you see here is a summary of the first stage of my data analysis. As you can see, I had categories such as communication as well as groupthink. How could you have groupthink without communication? And so those might have gotten blended together somewhat. Altogether, I had over 1,000 notes at this point, and about 20 or 30 categories. Let me tell you, at the beginning, it just didn't seem like there was going to be any consensus whatsoever. But after I'd spent weeks just going through these notes and over and over and over again, I realized that there was actually something behind the scenes. If you've ever heard the parable of the blind men and the elephant, it was very much like this. The nature of research is such that you get very, very focused on a very small piece of the process. It's very much like being blindfolded and being able to explore an elephant only with the tip of your finger. And so one researcher says it's a spear because he's touching the tusk, and another one says it's a rope because he's touching the tail. And only as an outside observer who's trying to get an idea of the big picture do you say, those are the same thing. It's an elephant. However, there's a very good reason why it took so much effort for me to realize this. There were two big pieces that got in the way. Number one was an issue of epistemology. On the left, you see Ginsberg and Co. talking about math as if it was this real thing. We call this Platonism, as in Plato. On the right, we see Sinclair talking about math as a sort of game invented by humans. This formalist opinion about the nature of mathematics is mutually exclusive, and there was no way for me to combine these two except to take what's called a post-epistemological stance. That is to say, I'm not going to ask the question, is mathematics real or not? What I'm going to say instead is that it doesn't matter whether it's real or not, because humans act as if such a world exists. Whether it's virtual or inherent doesn't matter. There is some kind of world that humans behave exists. The other big problem was with definitions, and there's no example more stark in contrast than between Bonato and Rasmussen, Zendaya, King, and Teppo. They're both defining here mathematization. And in both cases, they say mathematization has a horizontal component and a vertical component. But as you notice, Bonato says the vertical component of mathematization is about organization, whereas Rasmussen, Zendaya, King, and Teppo say organization is the horizontal element of mathematization. Ugh. Okay, so you take a step back and you say, they're both right. It's just that they've arbitrarily selected horizontal and vertical. So in my results, I got rid of the horizontal and got rid of the vertical and just kept the mathematization. Likewise, I took other definitions that were similar and overlapping and simplified them into something that pretty much everyone could agree to. The result of all my effort was the model you now see before you. This model takes elements from all of the research that I could find, which was about 180 articles in the end, and pieces them together. It started out as if someone had taken a jigsaw puzzle, shaken it up, and thrown it on the floor, and each article was one piece of the big puzzle. So one author would talk about this concept of mathematical community, and another one would talk about this concept of definition, and they would use words like intuition or justification, and it wasn't clear how all the pieces fit together. At least not until I realized that in almost every single article they used a phrase something like, students make sense of data. Make sense of, sense making, over and over and over again. And while out of the 200 or so articles, only one actively discussed sense making as their research focus, they all used that phrase in there somewhere. Ah! This was the solution to my jigsaw problem. It was the central piece to which all the others could connect. After taking into account warnings by several of the author not to use a linear model and to consider cycles and not to consider hierarchies and this, that, and the other thing, eventually I developed the model you see before you. It's important to notice that the orientation of this is arbitrary. The selection of shapes is arbitrary. It's done for aesthetic purposes. The important part is that sense-making is the central piece. If you forced me to make a decision and say one piece is mathematical thinking, it's sense-making. That's where mathematical thinking, you could say, yep, it's happening. All the other pieces happen naturally, but it's only when you put them together through sense-making that you're doing mathematical thinking. The other important thing to understand about this model is that you see some of these are solid lines and some of them are dotted lines. The solid lines are what I consider to be mathematical thinking proper. The dotted lines are pieces that are not really part of mathematical thinking, but in the practical real world, you just don't get mathematical thinking as we understand it without these. For example, you could not do all of mathematics entirely by yourself. It just would take much too long. So you have to take some of mathematics kind of on faith from other mathematicians. I call this pre-mathematized information, for example. The question you're asking yourself now is, so what? Well, there's actually practical classroom application for the development of this model. We have lots of research out there that talks about common misconceptions that students have, such as multiplication makes things bigger. But we don't have as much research on where those misconceptions come from and what to do about them. This model provides a basis for a teacher or a researcher to say, okay, I think this is the cause, therefore this is what I'll do about it. For example, many times when learning multiplication, a student hears from a teacher over and over and over and over again, multiplication is repeated addition, multiplication is repeated addition. And in this way, the student is reinforced externally by the teacher this concept that multiplication is simply a shortcut to addition. And we know that addition means more, therefore multiplying also means more. Okay. And that's a social-cultural cause for this problem. Another cause might come from abstraction. It might simply be the case that every worksheet that this student has ever done involves cases where multiplying does make bigger. Didn't see any multiplication with fractions or with negative numbers. In those cases, then maybe he could see that multiplication can make smaller. Another option comes in the form of justification, and this might come from a gifted student. You say, multiplication doesn't always make things bigger. Consider multiplication by fractions, such as a-bths times c. But this student says, nay, a-bths is really a divided by b, and a-bths times c really means a times c divided by b, and it's the division by b that makes it smaller. So in this way, the student has come to a mathematization such that a-bths is not an independent entity, it's a process of division. Another option might come from intuition, and I think this one, in this particular case, is likely the most common. The word multiply in English means to duplicate, and to duplicate things means you get more of them. Well, okay, obviously multiplication then means you get more, you makes bigger. In these ways, you could come up with specific causes and specific curricular interventions to come to a resolution that is meaningful. Another more philosophical consequence of this dissertation is the question, well, is everything mathematics then? And I make this possible argument by considering statistics. Some mathematicians consider statistics to be a form of mathematics. Some mathematicians think statistics is not part of mathematics, that it's more like physics, it's a form of applied mathematics. And by examining the way people talked about statistical thinking, I saw that it was basically the same thing as mathematical thinking, except there were a couple of different assumptions and underlying principles. So if you're going to say statistics is mathematics, well then you could say all of science is mathematics. And here you can see a webcomic from XKCD that illustrates this possibility. While my dissertation did not come up with a definitive answer to this question, it did create this question, which was something I'd never considered in the first place. I had never thought science and statistics and mathematics really might all be different incarnations of the same thing. They might all have the same structure, and we just put different names on it because we put different collections of facts in them. Thank you very much for watching this video. Make sure to click the link to go see the question and answer section of this presentation, where my dissertation defense committee asked me lots of really tough questions and I gave some really good answers.